An ultrasonic transducer is a device that converts electrical energy into high-frequency sound waves, as well as converting sound back into electrical energy. In automotive applications, we typically refer to piezoelectric transducers as sensors. The crystals used in piezo devices change size and shape when current is applied. Since piezoelectric materials also generate electrical current when force is applied to them, they can also work as ultrasonic receivers. Ultrasonic sensors can detect targets and alert the driver immediately. Sensors can be designed to produce a digital output for detecting the movement of objects, or with an analogue output proportional to the object's distance. Ultrasonic sensors convert ultrasound waves to electrical signals or vice versa. Those that both transmit and receive may also be called ultrasound transceivers. Some systems use separate transmitters and receivers, while others combine both into a single piezoelectric device. Ultrasonic transducers work at different frequencies in the range of 60 to 850 kHz. As the ultrasonic frequency increases, so does the attenuation of the sound waves in the air. Ultrasonic sensors use a piezoelectric ceramic to produce ultrasonic waves. The ceramic is connected via electrodes and is actuated by a control from the module. It then operates as an emitter for sound waves into the air. The sound waves are then reflected back from an object, so the transducer will also serve as a receiver by switching to receive mode at specified intervals, and then convert the sound waves back to an electrical signal. Basically, it converts electrical energy into sound, and the returned acoustics back into electrical energy. The ultrasonic pulses that are generated and reflected by an object are known as the propagation time of sound. The control module measures the time lag between the emitted ultrasonic pulse and the received echo and calculates the distance to the object. The sensing range of an ultrasonic sensor will also depend on the surface properties and angle of the detected object. The longest sensing ranges are achieved with objects that have a flat surface positioned at exact right angle to the sensor. Very small objects, or anything that partially deflects the sound, will reduce the sensing range. The easiest way to understand how ultrasonics are used in automotive applications is to see the signals on an oscilloscope. The control unit sends a very fast pulse to the sensor assembly. This is the ping that is converted to ultrasonic sound waves and projected from the piezo element. The ping must be very fast. It is pulled to 5 volts from 0 for about 10 microseconds and is repeated every 40 milliseconds. With no target for the ping to bounce off, the receiver sensor will not detect an echo, so its output remains at a steady 5 volts. As soon as a target is in range, the receiver sensor begins to pull the 5 volt signal to ground. The closer the target, the faster the return echo, so we can see the pulse width on the trace getting shorter. The vehicle's control module is able to interpret this echo time as a distance to the target and can then output a corresponding audible alarm. With TFT screen technology now in most vehicles, we can use the output from the ultrasonic sensor to display a graphical representation of any objects in the sensor's range. The hardware remains the same, but software is written to use the sensor output signal as input data to a graphical display. In this instance, we can view distance and angle, as well as determine a simple shape of the target. From parking sensors to self-drive cars, ultrasonics are here to stay. Knowing how this technology works will prepare you for the future. Thanks for watching.